is AERO 304. Welcome to Lab 3, Cylinder of Doom.
So in this video, we're going to talk about what we're going to measure in our experiment, what we expect our results to be, our methodology, and how we did the experiment. We're going to talk about the results that we found, any problems that we had, and then finally we're going to round it off with the data analysis.
We hypothesized that no tripwire will have our coefficient of drag greater than if there is an actual tripwire. So along with our hypothesis, we also wanted to look at angle separation, and we also think that with no tripper, the angle of separation will be less than if it does have a tripper. So our experiment has some everyday applications, such as a tree on a windy day, or even a pipeline through turbulent water.
So as you can see here, this is the wind tunnel. In the middle is our cylinder of interest. And then in order to see the flow around the cylinder, we have a smoke machine here that which the smoke went into this smoke distribution rig, which evenly distributed all of the smoke through the wind tunnel and into the test section. And then once in the test section, the smoke was illuminated by the laser sheet device, which allowed the smoke to be better seen by the human eye. And through that, we were able to see how the cylinder affected the flow through the test section. So here you can see a free body diagram of the cylinder looking into the test section. In the Y direction, we have the force of reaction from the walls in the Y, and then the force of gravity in the negative Y direction. Now in the X direction, we have the force of the reaction of the wall in the negative X direction, and then the force of drag in the positive X direction. One thing I want to point out is the difference between the force of drag due to friction and the force of drag due to pressure. Some assumptions that we made during our testing were that the flow was incompressible, that it was also steady, and that the wind tunnel was isothermal.
We studied relationship between coefficient of pressure at different points around cylinder and Reynolds number. We controlled Reynolds number by applying boundary layer tripper in the front edge of the cylinder, and to ensure reliability, we collected data at 4 different RPM regimes, so 100, 200, 400, and 300 RPMs, and then we collected second round of data going from 400 down to 100 again.
In order to better visualize the flow, we used a laser sheet and portable floodlights that shined on the flow in order to see it as it was moving through the test section.
So we started out last time having our smoke machine have to manually be moved when we were trying to get the smoke over the cylinder with an even flow above and below it. However, thanks to some great engineers, we got this lovely rig hooked up so that smoke would enter down here and then evenly distribute between the different pipes and flow through our wind tunnel.
One of the issues that we ran into while we were doing our testing had to do with the pressure ports reading the incorrect data. They needed to be plugged in properly in order to get the data that we were looking for and to give us correct coefficient of pressure graphs.
While troubleshooting why we weren't able to get correct pressure data on all of our pressure taps, we had to blow into the pressure taps individually to check to see which ones were working.
Total force due to pressure drag on the cylinder is an integral of pressure around cylinder over the surface area of the cylinder. We can approximate total integral by summing pressure readings multiplied by area of the panel. Since we only got 24 pressure readings, we will assume that the cylinder is a 24 multigone, and each area around the pressure tap is 1/24 of the total area of the cylinder. Here is the summation that we used for pressure drag. We know that pressure drag is also equal to half rho A times velocity squared times the drag coefficient. Our goal in this experiment is to find drag coefficient. So we sum all the forces due to pressure at each pressure port and set it equal to equation of pressure drag. Due to some algebraic rearrangements that we made, we come up with this equation for the pressure drag coefficient of the cylinder. To get standard deviation of these values, we use the following equation.
All error bars present in the graphs shown represent 3 standard deviations of uncertainty.
During data collection, we plotted coefficient of pressure versus angle to ensure that our data is accurate and there are no outliers present. As you can see, for most of the data collected, plots clearly show that with tripper, coefficient of pressure is lower than without the tripper. On the plot, black dots represent presence of tripper, red dots represent no tripper present. The blue line is a theoretical curve for idealized and visited floor. As you can see, 400 RPM gives the clearest results, especially in terms of boundary layer separation. On the 400 RPM plot, especially on the left side, we can clearly see that tripper changed boundary layer separation point. The boundary layer here has been separating about 15 degrees later than without the tripper. We summarized all of our data to show that coefficient of pressure due to drag changes when boundary layer tripper is applied. This last plot represents free stream flow velocity versus pressure of drag coefficient. Red dots represent no tripper applied, black dots represent boundary layer tripper applied to the cylinder. As you can see, the low velocity data points are not conclusive due to large error, while the high velocity data points clearly show that coefficient of pressure drag is significantly lower when boundary layer tripper applied versus when boundary layer tripper is not applied.
So for our next hypothesis, we looked at the flow visualization. And for this, we looked at Reynolds numbers. So what we expected to get, we used our Reynolds numbers calculated out here. And our overall visualization of the flow should look something like this. So let's take a look at what we actually got.
When the wind tunnel is running at 200 RPMs, it is creating a flow velocity of 7.8 meters per second. As you can see in the video, the wake regime is as we expected, having a cyclical pattern.
At 300 RPM and about 13.1 meters per second, we still observe cyclical wake behind the cylinder.
So at 400 RPM, or approximately 17.5 meters per second, what we expected to have was the same sort of wake as our 200 and 300 RPM. However, this was not what can be seen in the video. As we see in the video, it's more of a transitional Reynolds number where the wake is almost disorganized or chaotic.
Here is our data table for a pressure drag experiment. We completed the experiment at 4 different RPMs. For 400, 300, and 200, we observed reduction of pressure drag when boundary layer trapper is applied. But for 100 RPM, our data is inconclusive. So in 3 out of 4 cases, we met our expectation, and for 100 RPM, we cannot conclude anything. Here is a table of results for our flow visualization experiment. We observed 4 regimes, 100, 200, 400, and 300 RPM. We expected to see cyclical pattern for all of them, and as you can see from the data, we didn't actually observe cyclical pattern for 400 RPM. So we met our expectation for 100, 200, and 300. But for 400 RPM, we can clearly say that our expectation was not met.